Welcome to Spatial Patterns of Gold Deposits in the Gundagai region, New South Wales, Australia. One will note that the copyright for this presentation is 2005, so it's approaching 20-year-old information. Much more recent exploration on this prospect can be seen at the various URLs presented on our YouTube channel shown above. This presentation is prepared as part of the research titled The Spatial and Temporal Distribution of the Metal Mineralization in Eastern Australia and the Relationship of the Observed Patterns to Giant Ore Deposits. The Gundagai region is located in the very southeastern part of New South Wales. The geology of the Gundagai area is typical of the geology for southeastern Australia. In the Lachlan Foe Belt, the rock types are predominantly Ordovician to Silurian granites, volcanics, and sediments. The 22,240 gold deposits of southeastern Australia. A clustering algorithm known as AutoClust was used to look for patterns within the gold deposits of southeastern Australia. This algorithm is excellent in that it automatically extracts boundaries based on Voronoi and Delaunay tessellations. Human bias is minimized because parameters are not specified by the user in this automatic clustering. All clustering operations take place on the Delaunay tessellation or diagram, where data points become vertices and edges connect pairs of points to model spatial proximity. The m-value, shown in the following slides, designates the lengths of edges in units of standard deviation away from the global mean, which are included in a single cluster. The global mean is determined from the edges of the entire data set. The noise index of a point P is the ratio of the local mean over the global mean, where local mean is determined from the mean of points with edges incident to that point P. The noise index is a measure of the deviation of a single point from proximal points. The mean of edges incident to noise tends to be significantly greater than the global mean. Clustering of the gold deposits of southeastern Australia at an m-value of 3.5 and noise equaling 1%. Note that 6 distinct clusters can be distinguished at these settings. When the noise is diminished to 0%, it is much more difficult to see the 6 distinct clusters. Polygonization of the 6 clusters, with the Gundagai area region especially noted. A geology map of the Gundagai region. Please note the deformation of the ophiolites, which are in green. Geology map of the Gundagai area, with the gold deposits shown as yellow circles. Gundagai area, showing both the deposits, the Delaunay and the Voronoi tessellations. Gundagai area, gold deposits, and Delaunay tessellation. Polygonization. Considerable information has been lost about the patterning of the gold deposits in this area between the Delaunay tessellation and the polygonization. However, there is considerable evidence that there has been post-pattern dislocation in the Gundagai area. The following movie shows a reconstruction of the Gundagai area. Note these selected features in the Gundagai area. 1. Sinistral faults. 2. Arcs of gold mineralization. 3. Ophiolites. The Gundagai area has been reconstructed by a plus 20 kilometer dextral movement along the major fault shown as number 1. Note that the two arcs of gold deposits that were located northeast and southwest of the fault are now coincident, forming a single circle. Following are the clustering results of the gold deposits in the Gundagai area after the plus 20 kilometer dextral movement along the fault. The Delaunay tessellation. Polygonization in the Gundagai area after dextral movement. Polygonization in the Gundagai area before that dextral movement. Note the radial trends in the gold mineralization. Note that the radial arms, indicated by the blue arrows, show where the ophiolites have changed direction. The bend in the ophiolites coincides with the blue arrows. In the following slide, the geology has been removed, and we are left with polygonization, radial trends, the major fault, the ophiolites, and the circle of the larger gold deposits. The bends in the ophiolites and the radial distribution of gold deposits becomes even more obvious in this map. The Adelong goldfield is located on the western edge of the reconstituted circle. It had bonanza gold grades, 45 to 60 grams to the ton. At least 25 tons of gold came out of this quite small gold field, and it was one of the world's major producers for almost 60 years. Exploration at our Idleway prospect. Location of the Idleway prospect. This is a Chim gold anomaly map for the Idleway prospect. This data was collected in the early mid-1990s, and a much more comprehensive and available technology is now available for similar results called mobile metal ion. CHIM is a Russian acronym, and for those interested in a historical approach to geochemistry, here's the definition. This gravity map of southeastern Australia shows that the Idleway Prospect is located on a local gravity high. This was the extent of the gold anomalism with near coincident copper anomalism in 1995. This map shows that the Black's Flat diorite occurs in the crest of an anticline. All porphyry copper-gold deposits in southeastern Australia are proximal to Ordovician and Silurian Shawinitic diorites. The Black's Flat diorite at the Idleway Prospect is of this type. This map, which is at the same scale as the previous map for the Idleway Prospect, shows that the Grasberg, world-famous Grasberg gold copper deposit, also occurs within a diorite in the crest of an anticline. These total production figures for Grasberg are indeed impressive and shows it to be one of the world's giants, world-class gold-copper deposit. The Grasberg-Erzberg porphyry copper deposits contain more than 30 million tons of copper and greater than 2,700 tons of gold. At a conference held in Sydney, Australia in 1995, Dr. Doon Wyborn, who worked at that time for Geoscience Australia, made the following statement, quote, "Could a Grasberg-like system be found in New South Wales? The answer is, there is no reason why not." Thank you. References.